Um, Welcome to the stream today. Today we're going to go back to this kernel thing and try to use a for generate loop to make sure that our line buffers are BRAM. Currently they're not BRAM. I went through synthesis and it gave me an absurd utilization. I'm using 1,000% of the FPGA to utilize these line buffers because they're all done in LUTs. So today we're going to figure out how to infer the BRAM correctly. And to do that, we need to be a little bit specific. So what we're going to do is we're going to forget all about that fun stuff. And we're going to do a for generate. Let me get my reference up here. So we're going to do a for generate. And we need to put in the things, right? So let's go back here. Now I guess we can give it a label. We're going to say line gen, right? For I from 0 to kernel size -1, probably would be in. Okay, and we're just gonna say for, right? We're gonna have it n generate. I think we have to put the name line gen, right? Cool. And now this is the generate takes concurrent statements, but we want to get, so we want separate clock processes. And we're gonna want, I'm gonna want a quick vector. So we're gonna do type. We don't want type. We don't need type. We're just gonna go here, signal. Write enable, right? Write enable vector. And it's gonna be a standard logic vector forward down to 0. Begin. So we want to, yeah, we'll fix it later. So we're gonna say if rising edge of clock, then end if. So first thing, we're gonna have it read out. So we're going to do a read out. So we're gonna need a vector of there's a line buffer. So we're gonna have our output. So let's do a type. So yeah, let's do a type t line out is array 0 to 4, right? Of the output of these things, and they're going to be a standard logic vector of 7 down to 0. Okay. Now we're going to do a signal line out, and it's going to be type t line out, right. So line out of I, line out, yeah, of I is going to be line buffers of I. We'll worry about that later in reorganizing them. Of x count. So we're unhappy right here. Oh, it wants this to be like 2 integer. Now, so, and then if write vector of I equals 1, and it should be a 1-hot state machine, so I'm not too worried about it. Oh, we should, but then and if, and then we're going to say if this is true, taking the same value, right, is going to equal gray, right, it's going to equal gray. So now we've done our generate here, and this should hopefully generate BRAM. So to test this real quick, we're going to create a quick process. Right, and we're going to do rising edge of clock. And what we're going to basically do is just x count equals x count plus 1. But if s count equals 1919, right? 1920 minus 1. And if x count equals others 0. You wanted that, I assume. And okay, and then we need to associate the window value. So let's do window 1 equals line out 1, right? Well, we probably can start with 0. 0, 2, 3, 4, 4, 3, 2, 0. Okay. Let us bring up our sources. Line buffers working. So let's see if this creates BRAM, and I hope it does. Otherwise, we're going to have to get more creative. Let's do it. So, issue last week is when we tried to infer the multiple line buffers the way we did, it did not use BRAM. It used kind of the flip-flop memory. And the FPGA does not have enough flip-flop memory for 5 line buffers of 1080p or 1920 by 5. Not have enough flip-flops for that. And because we did that, it used up 1000% of the FPGA, which is not 9x more than what we have. Or no, yeah, it's not possible. So right here, see this beautiful statement right here? Implemented as block RAM. So by wording it differently, oh look at that, it did it in 3 seconds rather than 6 days like it did last time. So this is important when we're dealing with this, when we're trying to infer memory. We have to understand our synthesis tools. The synthesis tools matter very importantly. And we're trying to create code here that is cross-platform, that we don't have to write down the primitive of the memory unit we want to use. So, I mean, luckily, hopefully for Xilinx, this infers the BRAM. Hopefully, if you want to use something else, it would infer the local memory instead of trying to use flip-flops. So we just report utilization, and instead of the 1000x summary it gave last time, we're only using 1% of the BRAMs for our different spaces. I'll go back to that log. Where's that log? Decloning instance. So somehow I put it on one DRAM. Wonder if it made it wider or something. Well, I mean, it's only 8 times 5, right? So in this instance, it would only be one memory unit. So let's play around with this real quick. I'm curious. So let's go back here. Make that a for loop. And we want to do kernel size -1, kernel size -1, kernel size -1, kernel size -1. Okay, so we got good there. Now let's write a quick for loop here. And you know what? How about we just stick it here, you know? I. There we go. Cool. So, shall we see if that works? Let's go ahead and set it to 10, right? Let's see how 10 memory units are inferred. Oh, and we don't never do anything. Let me go back here where we have this right vector. I want the right vector, which is kernel size down to 1, is going to be kernel size down to 2, right? And kernel vector size -1. Okay, we're happy with that. Let's run synthesis. I want to see what this will turn out, because before we said we could fit into one small BRAM. We might have to go in and try it with 5 again now that we added this vector thing that's changing. I had to close this design. Now let's go look back at the log. So we are inferring it correctly. The right enables. Yeah, let's go ahead and open the synthesize design real quick. Do a utilization report. If it says 1 BRAM again, I'm gonna be like, eh. Okay, it says half a BRAM. Makes me question this log. Are we actually working as we expected? I mean, maybe it's just writing the same output to all of them. Well, how about this? Instead of trying it, let's go look at this net list, right? So we have a leaf cell. It's going to be, where is our beautiful BRAM leaf cell? Maybe I'll have to find the net that does it. Yes, there's 100 of these window things. Let's go figure out how it's done. Carry, carry, carry. Where's my VRAM? We go follow where gray is being. There we go. Let's just go follow gray down the rabbit hole. There's no logic here. I feel like something was simplified a little too much. How are we doing the addressing? Do we have a enable? Right enable, right? So let's go back to line buffer vector. We're gonna. This is just gonna be equal 1, 1, and others, right? Because it's defaulting to 0. Need to put this down. Let's see. How do you do that again? How do I do variable bits? Shifting's right. Guess we could put like a reset in here. Synchronous reset. Gotta reset. Oh, how am I gonna do this? Let's see, VHDL others with concatenate of others. Okay, so we want to do what? A 1, comma, others 0. Okay, that's what I want to do. And then we want to rerun synthesis. And better see something on that right vector. So beforehand, the synthesis saw that the right vector was never being initialized to a value, so it was automatically initializing to 0, and they were all 0, and they're never being written to, so we were just reading the BRAM. And I guess it connected the input, so it was never writing to the input, which was confusing. There we go. We got 10 RAMs. Okay, so let's look at this to see how much VRAM we have accessible to ourselves. So let's report utilization. Now that the write enable is actually being initialized to a value and shifted, we see that we're using 10% of this. So we're doing a 10 by 10 line buffer, which is pretty good. Only using 10% of the FPGA, plus the additional other line memories and whatnot. Let's go look up our current project, right? Can we go stream DVI2? Yeah, let's go look at this project and see what the utilization is. I'm curious to see how much wiggle room we have. Because I think the plan was I wanted to have two right next to each other in the same design. I wanted to have an HLS 5x5 grayscale and then have a HDL 5x5 grayscale. Compare the results, compare them, run them both, and be like, oh, look, this is the HDL one, this is the HLS one, and they produce the same result. And though we spent 5 weeks or whatever, how much time to get the HDL one, and we spent a few days to get the HLS one running. HLS one took a lot faster, but it'd be interesting to see the latency difference and the utilization difference. So let's go ahead. We should be able to go pull this up right here. Table. So we're using only about half the VRAM. So yeah, we could essentially, I think this is with a 3x3 multiple color one. So we'll have to look at the utilization difference on those. But we essentially could have about, let's go back to this one real quick. Let's go ahead into our type and drop this back down to 5. which should only be a 5%, right? So it's a drop to 2.5 maybe. So 2.5. We have a remainder of, we're only using about what, half on the DVI one background. Only using about half on this guy. Yeah, half. So we could do several line buffers in a row. Okay, the final thing, let's pull up HLS land. See what our current HLS design does in memory utilization. That should help be useful. Yeah, go ahead and open that. Let's go open this kernel. I think the kernel is set for 3x3, but 3 different colors. So I think so there's a line buffer for each one. We'll have to look at it and make a good guess of what it would be here. So let's report utilization. Summary. So yeah, we're using about 5% or 2.5. So currently this one we're using a total of 16, but let's look at our solution to figure out what the difference is. So this one, we are doing a color for each of them, right? RGB. And so we have so yeah, so it's 3 times the size. So we're dealing with 24-bit. 24-bit times 3. So let's say calculate real quick, right? So we have a 2.5. Let's go to standard, right? 2.5 divided by 5. So you get 0.5. Here we have 24. So what we're going to do is we're going to do 3 times 3, suggesting that we have 9. And we go to solution. And we got about 16. So we got 16 divided by 9. So we got 1.7 to our 0.5 usage on our other system. So this is interesting. This is suggesting that our HDL is getting much better utilization, almost a 3x improvement over HLS in using our DSPs. And in all honesty, our DSPs may be our limiting resource. We'll have to see. We'll have to combine it with our flip-flops later to see what our flip-flops and LUT design is. Okay, so that's interesting. We may have to close off early. I have to go take care of something. But so we have the line buffer outputs, and now we need to associate with a window and then shift the window, and that should be good. So I think we got this hard part, and this thing we can write real quick next time, and get the shifting window working. Once we get the shifting window working, we need to pass through the valid signal. That's one thing I haven't done, is a valid in and valid out, and just have the valid chain through all of this, and just have the valids connect, because the valids are very important. Also, we have to do the beginning of the frame and end of the frame. Do we need to do that? Yeah, we need to have the beginning of the end of frame, so the X and Y count are updated. We may have the X and Y count be updated in a different module, which may just be easier. I'm trying to think of a better way to do the valid. Maybe we just add a, yeah, I don't know. Yeah, we'll just have to see how it works. Well, thanks for watching. I know this is a short video, but hopefully we've got 1 day. We have 1 day to do, finish up those windows. That should be easy. Have another day to work on the valid signal and work on the XY coordinates, and just resetting that value. Yeah, we should probably do it in that system, and then we should be good to go. So that'd be about, I think we'll spend 3 more days on the HDL. Oh, we have the AXI interfaces, which maybe take a day, so maybe 5 more days on the HDL, and then a day to get the HLS working, and then another day to compare them. So I'm gonna say 2 more weeks on this project, on this chapter of work, and then we'll move on to something new. Thanks for watching. I'll see you on Monday. Hopefully we'll spend a little bit more time on this. Bye.